Welcome everybody to the Boundary Layer Seminar, Boundary Layer Urban Meteorology and Land Surface Processes Seminar, old seminar for short. Today, my PhD student Elizabeth Spicer is going to give a talk and overview of some of the work that she has done related to urban heat island development in the Houston area. Elizabeth joined OU in 21, correct?
Yes, I think.
Okay.
Yeah. It's been a while.
And completed her master's, also related to work in Houston, but a completely different instrument, completely different focus. She looked at CO2 measurements that she did during the Tracer campaign. She defended her master's in summer of 23 and has then moved on to look at the heat island. She's giving us an update today.
All right. Thank you, everyone, for being here today, especially with a visiting professor's talk going on. So very much appreciate all of you all. So yes, I will be talking today about the urban heat island. So for those of you all who are unaware about the urban heat island, it is essentially the general phenomena where temperatures in urban areas are higher than in rural areas. And you can look at this from multiple perspectives, and they're all related, but not the same. So you can have subsurface urban heat islands, as well as surface layer, boundary layer in the atmosphere, as well as urban canopy layer within the boundary layer. So, of course, if you look at the most built up populated spaces within an urban area, that is where within the atmosphere, near the surface, you are going to have at night in particular, the most elevated temperatures. So I am today going to be talking specifically about the urban canopy layer, urban heat island, which is typically measured at around 2 meters in the atmospheric boundary layer. And as Petra mentioned, I will be looking at this within the Houston, Texas area. So the reason that I'm looking at this is because of the very large DOE armed tracer campaign, which took place from October 2021 through September 2022. There was a very intensive operational period during 2022 where there was a collaboration between many universities and organizations which had instruments in the area taking measurements for a variety of reasons. So Houston is a very large city. It takes up a massive area at the Gulf. A lot of people live there, and there are also a lot of petrochemical facilities and plastics manufacturing that occurs there. So everything is just kind of all sandwiched on top of one another. So the people living there not only have to deal with sea breezes and bay breezes and the nice, lovely Gulf Coast moisture, but then they also get to be next to a bunch of processing and all the joys of that. So prior UHI studies in the Houston area have shown mean summer urban heat island intensity can be around 2 degrees Celsius, whereas you can see maximum urban heat island intensities of up to 10 degrees Celsius. But these are typically done, or these studies have been done with a traditional urban heat island intensity, which I will get to in a few slides. So the motivating factors for this study are first and foremost human impacts. This is not talked about so much in traditional literature. However, I want to make a point to make it a part of my conversation here today. So prolonged heat exposure can have adverse health effects. And even if the magnitude of the heat that people are experiencing is fairly low, if you're experiencing it day after day after day, it adds up and it can have a toll on your health. And namely, if this is happening at night, if you have really high temperatures during the day, say you're going out and working outside and you come back home and you don't have air conditioning or you don't have adequate air conditioning, you're unable to cool down at night from the exhaustion you might be feeling during the day, that can be especially difficult for your body to recover from. And this has been linked time and time again in human health studies to increased risk for heat-related illnesses. And in recent years, there have been many studies that have shown that heat vulnerability has been tied to things such as age, economic status, and other socioeconomic characteristics that have been related to disparities in economic status, as well as related to minority subgroups. And specifically within the United States, this is actually tied to the historical practice of redlining, unfortunately. So this is a part of our history, and it still shows up today within the science, and it is still impacting people to this day. So it's important to talk about. Second motivating factor for this study is to have an analytical, scientific approach for determining heat risk. So as I mentioned a couple of slides ago, traditional methods for looking at urban heat islands typically look at the urban heat island magnitude as a simple gradient. So this is called an urban heat island intensity most often in literature, and it is simply a gradient between at least two data points. So you have one temperature measurement in an urban area and one temperature measurement in a background area. And the difference between those is your urban heat island intensity. This is a lot more simple than it sounds. Urban heat island intensity does not explain the temporal or spatial variability that an urban heat island can have, and it does not at all address how it can impact people. So, and if you only have a couple of temperature measurements, you simply cannot describe how complex things can get. If you have a few more temperature measurements, things can get a little bit better in your description of the urban heat island, but oftentimes you don't have the ability to control where those measurements are taken. So you're kind of out of luck as far as that's concerned. So oftentimes studies can be kind of limited in how you describe the urban heat island in areas, making your potential applications for what you learn from them a little limited. So we want to make a scientific approach that takes a little bit of the subjectivity out of it if you have the ability to choose where you're taking your measurements, and also gives you the ability to understand more of that spatial and temporal variability that I was referring to. The third approach is to create a more holistic approach with data and method choices. So trying to use, in the age that we are living in, big data and big data analytical methods. So we have these tools at our fingertips. Why not utilize them to actually learn more about all of that spatial and temporal variability that can actually tell us more about what's actually going on. And so this can actually unlock the potential to partake in predictive tasks for urban heat island and heat risk potential, and also benefit both of the previous two goals that I talked about. So getting into what I have been working on, the data that I have been working with is from NOAA's National Centers for Environmental Prediction, or NCEP, as you might have heard the acronym. So this is a reanalysis data set at a very nice high resolution of 2.5 kilometers in hourly data. And this is a very unique reanalysis data set in that it actually simulates near surface observations, which is fantastic for things like urban heat island. An example of some of the data in the Houston area is actually shown on the right. So you can very clearly see where the city center for Houston is. It's clear as day, even though this data was actually collected at night. Haha. Okay. So along with this data, I am actually using what is known as a local climate zone map. So some of you all might be familiar with this, but if you're not, I'll take a moment to explain. So of all the pretty colors that you see here, each one is associated with either a number or a letter. All of the numbers are associated with built local climate zones, and all of the letters are associated with more natural climate zones. So each of these is tied to very specific properties that relate back to the energy balances and budgets related to what's happening with our surface and with our near atmosphere. So I actually created the training data set for this greater Houston area and put it into a generator, which created this map in line with a system of data sets for cities like Houston for the globe. So this is harmonized for all cities, which essentially allows for a nice harmonization within studies like this, even though the methods at the end of the day might be a little bit different. And so as you can see, I selected different subdomains within my large map of the greater Houston area. And within this, I have 4 urban and suburban subdomains, and I have 5 rural subdomains. And I have a table with the top 3 local climate zones within each of these subdomains, but you don't have to really look at the details here. This is more, if you want the details later, we can talk about them. The heuristic here is essentially that the urban and suburban subdomains have at least 30% built climate, local climate zones, whereas the rural subdomains have less than 30%. So that's what we're essentially working with. All right. So in order to sort of down select the data, make sure that we don't have other factors at play that are potentially adding a bias to the analysis that I'm performing for my urban heat island analysis, I wanted to make sure that there weren't, for example, any synoptic effects that I was looking at on accident that were biasing the data. I first was looking at the campaign averaged diurnal subdomain temperature trends. So what you see here are for each of the subdomains, I have all of the hours within the tracer campaign averaged for, so for each hour, all of the pixels within the subdomain. So I noticed that during the overnight period, during the overnight hours, specifically looking at 2 a.m. through 8 a.m., all of the urban and suburban subdomains had higher temperatures than the rural subdomains. And this was consistent throughout at least the mean of the campaign. So these are in the green box. This was not present during any of the other hours during the tracer campaign IOP. And so we decided to select this time period for analysis, as this is where we would have the maximum urban heat island information content. So taking data from 2 to 8 local time, I put this information into a self-organizing map. So I'm not here to really discuss self-organizing maps in detail. If you want to, we can talk about that offline. But in a nutshell, self-organizing maps is a way to cluster data with the conservation of the topology, not topography, my apologies, the topology of the original data set. So each plot that you're seeing here represents the mean behavior over time within each cluster or node of the original data set. So again, that 2 to 8 a.m. time period within the data. So as your node number increases, so does the time average maximum temperature over land. So you can see this pretty clearly just looking at the color differential, but I've also listed the maximum temperatures on each subdomain or on each node for clarity. So as you can probably tell, node 9 displays the highest nighttime heat exposure. So you might expect that this is what we would consider to have the highest urban heat island from some perspectives, perhaps. So looking at the data set from a slightly different perspective, but still looking at temperature, we can also see the temperature variation. So while node 9 had the highest nighttime heat exposure, it has the lowest, or one of the lowest, node-based spatial temperature variations, whereas nodes 1 and 2 have very high spatial temperature variation. So this isn't exactly what you might expect to see, and might actually skew what we would think of when we think of a traditional urban heat island intensity. So what actually happens when we run the numbers? So calculating an adjusted urban heat island intensity, so using the urban subdomain temperatures minus the rural subdomain temperatures, we see a reflection of that variation, of the variation plots, where node 1 has the highest urban heat island intensity. And do note that these urban heat island intensities are not necessarily directly comparable to what you would see in literature, but this is due to averaging that we're seeing over time, and of course also over space, since we're looking at subdomains, not individual in situ stations. However, this does show what the data is actually showing us. It's just not necessarily what we would expect. If we were to look at random subdomains, like let's consider the coastal bay and the East Forest subdomains, for example, we would get something that looks like this, which I don't think is necessarily the best representation of the data. It says that for node 9, we actually have an urban cool island, which makes no sense at all. For what we would actually see in the data. Petra coined the term heat risk roulette, and I think that that sums up what we have here exactly. So actually making an informed selection of the data and using multiple stations for calculating your urban heat island intensity is important and a good lesson to learn through this analysis. But taking a step back from the concept of just using temperature in an urban heat island intensity calculation, does this really describe how people experience heat? I mean, of course, temperature is a part of the equation, but people also experience humidity and the effect of wind and also cloud cover and all of those things. So what if we consider heat risk metrics? So there have been many heat risk metrics that people have come up with over the years to describe how data can be used to attempt to essentially formulate a way to calculate the effect on people. So each of these has many different assumptions associated with it, and very complex formulations. And the results from these different metrics can contradict, which has led people to get really hung up on this problem and really not know which method to use and which method is best. But for the sake of simplicity, let's just take a look at heat index. So in the top right-hand corner, you can see the equation for heat index. So it is based on temperature and relative humidity. And this is currently what is used by the National Weather Service. This equation is the most common approximation of what was originally just a table that was formulated back in 1990. That is based on a model of heat transfer from the human body that makes a lot of different assumptions. So you might think of heat index as a way to just describe how people experience heat all the time, but it's actually expressing how people feel heat when they're walking, which I thought was an interesting assumption to take into account. And it also actually assumes wind speed, which is another fun little tidbit. So taking this into consideration, it's not necessarily a universal metric, but it is used in a lot of situations. So for the time being, let's just consider it something that we can apply universally and just take it with a grain of salt. So if we look at a sort of traditional urban heat island intensity, but apply heat index instead of just temperature, what do you think we would get? Well, I ran the numbers, and it turns out that if we look at the difference, we not only see that node 1 now still pops out as having is drawing attention to itself, but now nodes 8 and 9 also pop out as something that we should pay attention to. Why exactly would this be? So on the left, you'll see temperature, the same plot that we've seen a few different times, but on the right, now we have relative humidity. So if you haven't spent a lot of time doing field work in Houston over the summer, good for you, but for the rest of you, this is why heat index provides a little bit more context into the data. It's because relative humidity is very high most often in Houston during the summer. I mean, you probably could have been able to tell that without actually having to be down in Houston, but I digress. However, despite this benefiting our analysis, do all nodes exactly exhibit hazardous levels of heat index? So even though we have higher values of heat index necessarily, and we get, although differences in heat index tell us that nodes 8 and 9 are something that we should pay attention to, are we really actually seeing levels of heat index that we should even really be paying attention to? Well, some of the nodes say yes, but not all of them. So only nodes 6 through 9 actually have mean values of heat index at a great enough percentage that we should actually consider. But what if we actually consider the subdomains that we looked at previously? So if we consider the percentage of data per node in rural and urban subdomains, we can consider an alternative way to assess heat exposure. So this allows us to discount any of the gradient or difference methods that can give us some of the biased perceptions of what might be happening and what people might be experiencing. And instead, we get something that looks like this. So once again, this is a mean of just the rural subdomains in the middle row, and then a mean of the urban subdomains in the bottom row. And you can see the percentages of the pixels in those subdomains that have a heat index greater than or equal to 80 degrees Fahrenheit. And it is clear that the percentages are much higher often for the urban subdomains than the rural subdomains. So a couple of things to point out. For node 9, which often came up in discussion when looking at temperature, the heat index is high heat index is very common for both urban and rural subdomains. So do we have actually a heat wave going on in this case? Well, to truly say this, we actually need to have a temporal analysis to say this conclusively. But for nodes 6, 7, and 8, we still see a large disparity between the urban and the rural percentage of heat index above 80 degrees Fahrenheit. So these are some nodes that we can really dive into to get a greater understanding of what's happening and get a greater understanding of what are the conditions under which locals might actually be impacted, and get a greater understanding of also the conditions at which we could advocate to local government officials as to when they should open cooling centers, for example, or provide methods for helping people who don't have the ability to assist themselves in order to avoid heat-related health conditions. So diving into these 3 nodes a little bit, we can get a glimpse into what might be happening within the atmosphere. So on the top here, I have nodes 6, 7, and 8, just looking at the heat index in degrees Fahrenheit. And on the bottom, I have wind speed. So if you know a little bit about urban heat island analysis traditionally, you might know that wind speed is considered a controlling factor for canopy layer urban heat island analysis. So this makes a little bit of sense physically, because if you have calm winds, you don't have a tendency to want to transport the warm wind away from the source, which would be the urban centers. And so you're going to have a higher magnitude urban heat island. So for nodes 7 and 8, we have nice calm conditions present in the nodes. So it would make sense that these would have higher heat indexes for the urban areas. So this makes sense. However, node 6, we have more mixing and transport because we have higher wind speeds during this point in time. So why exactly are we seeing a higher heat index for this node? This doesn't necessarily make sense with traditional analyses with just wind speed alone, We need a little bit more data to truly understand this. So another piece of data that the URMA provides is wind direction. And so wind direction traditionally just dictates urban heat island shape. And we can actually see the influence of this a little bit in node 8, as we have a little bit of pluming effect happening that is reflected within the lighter colors from the city center advected to the northwest. So due to coastal proximity, we need a little bit more observational analysis to understand if there are other effects going on. There have been a lot of discussions related to sea breezes and bay breezes related to the tracer project, but the majority of the work with this has been done in the afternoon periods. So not a lot has been discovered in overnight effects that might be happening. So while we don't currently have, or I don't currently have, a working hypothesis as to what effects might be related to the interactions between land and Gulf air masses necessarily. I think that there's a potential that there's a relationship here that we could quantify with a little bit more data. So given this, we can get a slight bit of insight into what's actually happening within these nodes, but it's definitely clear that more data are needed. So given this, I will wrap up. So first, I want to start off by saying that URMA data and self-organizing maps provide very unique insight and a lot of utility, even though obviously there's more work to be done here. Traditional urban heat island intensity temperature analysis does fail to identify the strongest urban heat island signatures from self-organizing map nodes. And temperature data alone is insufficient to describe heat stress, which is really where we should be focusing, especially in the times that we are in, when climate change is exacerbating the temperature irregularities that we were already seeing. So opportunities do exist for non-gradient dependent analyses, which we should be focusing on as they can skew results, as was shown previously in this presentation. Though we do need to refine the methodologies a bit more before we settle on a specific recommendation for the field. But controlling factors for elevated urban temperatures appear to play roles in nodes with elevated heat index and urban subdomains. So as far as future work is concerned, this is only a portion of it, but what I do want to share is that there are other traditional urban heat island controlling factors that I want to explore. First off, cloud cover. So that is actually a product that the URMA has that I can analyze. So there, of course, are other data sets that I can use alongside the URMA as well that I am considering, but this is one that is readily available that I do plan to include in my analysis. I can also perform independent validation of URMA temperature products with other 2-meter temperature data that were not assimilated into the product itself to provide a little bit more confidence in the products that we generate. Additionally, I want to expand this analysis into the daytime periods to see if chronic low magnitude heat exposure that we're seeing at night during summer periods in Houston, how that magnitude of that actually compares to high magnitude heat exposure during the day. If we actually see, if we can quantify if one of them is worse than the other. I also want to do some co-analysis with other data sets. So here I've got the clamps trailer, the one and only, or one of two of only, on the left, and an ARRI instrument on the right as an example of an aerosol instrument that I might use. There were lots deployed during the tracer data set, and there are a lot of relationships between urban heat and aerosols. And then, of course, I also want to test this in other cities, because just because it works in Houston doesn't mean that that will make it work anywhere else. So having a product that we can use in many large cities would ultimately be the best for trying to expand this and ultimately create a product where we can predict heat risk, not just be able to analyze it for this one particular case. So because ultimately the focus of this is trying to help the people who are impacted by it, not just be able to look at some data. So with that, thank you all for attending, and special thanks to the other folks. So.
I don't know enough of that.
Yeah, I know.
Okay. So I really enjoyed your talk today. I have well, one kind of comment, and then the second one is definitely a question. So when you were talking about relative humidity, you were talking about at night into because obviously during the daytime of the summer, right, you're going to have high enough temperatures that your saturation vapor pressures. Well, not really close.
Sure.
So I just wanted to double check. And then the second question I had was, what do you expect to kind of glean from the cloud and aerosol?
So that's a great question. So going back to this, so cloud cover data, I think, is going to be very interesting. So once again, if you've spent any time in Houston, you would see this yourself. Pop-up clouds are notorious in Houston during the summer. They happen almost every single day. So it would be sort of naive to assume that, well, at least they happen every single day or during the day. So at least if we consider those during the day, or if we don't consider those during the day, it would be naive to assume that every single day was just a clear day. At night, I'm not so familiar with the cloud patterns. So I think it'd be at least interesting to explore the data set and to see how common they were, and just explore how they would impact the data. So if nothing else, just to look at the products side by side, looking at the heat index maps next to a cloud cover map. There is talk within my committee of looking at other heat metrics that include other data like radiation and cloud cover data. As I showed, it's going to take forever to go back to the pie chart, or not the pie chart, the Venn diagram. There we go. There are other metrics that I can utilize that would be more complicated to calculate, but it might be worth the struggle in order to more accurately represent what's actually, how people are actually impacted.
Two things. One, have you looked at the distribution of whatever variable over all your urban regions versus the distribution all over your non-urban? Because if there are normal distributions, there are things.
Yeah.
And second, you mentioned cloud cover and your data is at night, which would actually result in a heating effect.
Right. Yep.
Think that current.
So on the statistical question, I guess I should repeat for folks online. So the first question was, have I considered looking at the statistics of the data within my subdomains to see if there is a statistical difference within urban subdomains versus rural subdomains? And I have not done that yet, but that is a great addition that I should do, because if there is a statistical significance, that would absolutely be notable. So thank you for that. And as far as considering cloud data at night being a radiative heating effect, do I think that that's happening? If I remember properly, unless there's a synoptic event going on, I doubt that cloud cover at night would be likely, is my gut instinct. So I doubt that it is a major role. However, that's only my gut instinct. So once again, I would like to take a look at the data before I make that conclusion. So. Yep.
So a lot of this work today using URA today, folks balance this product doesn't how do you think results generalize those forecasting?
Okay, so how do I, okay, so let me repeat this and correct me if my recap is not what you're asking. So, so I got you. Thank you. So the question was, given that the URMA is not a real-time product, essentially, how would I generalize this to forecasting and essentially real casting, nowcasting? Hmm. Right. So the process that I've thought about. So first off, as I mentioned, I am wanting to do some comparison to in situ data that are not assimilated into the model. So that would be the first step, is making sure that what the URMA reanalysis is showing us is actually we're able to see in reality. So first off, does URMA match reality, at least to a way that we can characterize? So then the next would be to find at least nowcasting or forecasting product that matches close enough in resolution that we can at least quantify the bias between like the product and the URMA. So I think the closest in resolution would be the HER. And so we would have to try to quantify the bias between the HER and the URMA. So assuming that we could do that, it would just be a task of trying to then take HER data and then essentially run that through a SOM and then use the SOM in a predictive task. And I will say that I already have done a preliminary test using SOM data to then run through a predictive model and to then predict like SOM results. And I have gotten very good results with that, just to see if there was anything there. So assuming that we could find a nowcasting or forecasting product that would meet the criteria, I think that there's a path forward with this.
Just want to be caution.
Okay.
Each strip bar does.
Okay, yeah.
So if you're trying to remove simulation of observations, you may want to consider that.
Sure.
So the H strip bar typically does remove simulation. Black observation.
And I guess I would just have to consider the time in which the analysis product is created, assuming that it's faster than the URMA is created. So, but thank you.